Hello everyone and welcome back. In this video we're going to talk about the central limit theorem and the sampling distribution model for means. Now in the last video we talked about the sampling distribution model for proportions, but we can also look at sampling distributions for any statistic such as medians, variances, minimums, and etc. We mentioned earlier that under certain assumptions and conditions, the sampling distribution models for proportions will be a normal distribution. And this will be true for means as well. And this result is known as the central limit theorem. Now this theorem says that the mean of a random sample is a random variable whose sampling distribution can be approximated by a normal model if the sample size is large enough. And the larger the sample, the better the approximation. Before we can use the normal model as the sampling distribution for means, we need to make sure that the following assumptions and conditions are satisfied. These are the same assumptions that were mentioned earlier. The independence assumption says that the sample values must be independent of each other, and this can be assumed if they satisfy the randomization condition. For the sample size assumption, there are two cases to consider, which will depend on the population distribution. If the population distribution is normal, then its sampling distribution will also be normal regardless of the sample size. But for population distributions that are not normal, then we will use a rule of thumb which says that the sample size must be at least 30. So let's look at an illustration of the central limit theorem. Consider rolling a die 10,000 times, and we plot the following histogram. So here we have the population distribution, which is a uniform distribution as the heights of all of the bars are nearly the same. Now let's consider rolling 2 dice and then taking the average of the die rolls. So here, the sample size is the number of dice, which is 2, and it's not the number of rolls. So for a sample size of 2, this is the sampling distribution for the mean of 2 dice. And we see that this is a triangular distribution. Now let's consider increasing the sample size or increasing the number of dice. And we're going to take the average of 3, 5, and 20 dice, and we obtain the following histograms. Notice that as we increase the sample size, then the sampling distribution looks more bell-shaped or more normal. And the larger the sample size, the better the normal approximation. And this will be true regardless of the original population distribution. So we started with a uniform distribution, and as we increase the sample size, the sampling distribution model looks more and more normal. And so this result is known as the central limit theorem. Now if we're working with very extremely skewed distributions, then we may require a larger sample in order for the sampling distribution model to be normal. And so we use the rule of thumb where as long as our sample size is at least 30, then the sampling distribution model will be normal. If we're working with extremely skewed distributions, then we may require a larger sample in order for the sampling distribution to be approximately normal. And so for populations that are not normal, then the sample size should be at least 30. But if the population distribution is normal to begin with, then its sampling distribution will also be normal regardless of the sample size. Notice as well that the spread of the sampling distribution model gets smaller and smaller as we increase the sample size. So the central limit theorem gives us the sampling distribution model for means. When we take a simple random sample from a population that has a mean of mu and a standard deviation of sigma, then its sample mean will have a sampling distribution which has the same mean as the original population. So the mean of the sampling distribution is mu, but the standard deviation is given by sigma over the square root of n, where n is the sample size. So we can use standardization, as before, to find the probability for the sample mean by using the z-score for y bar. So the z-score is given by y bar minus the mean of the sampling distribution model divided by the standard deviation of the sample mean. So let's take a look at a few examples of using the sampling distribution model for means. Assume that the duration of human pregnancies can be described by a normal model with a mean of 266 days and a standard deviation of 16 days. Now, what percentage of pregnancies should last between 270 and 280 days? So here we assume that the distribution of human pregnancies durations is normal. It has a mean of 266 days with a standard deviation of 16 days. And so the center of our model is at 266. And we want the percentage of pregnancies that last between 270 and 280 days. So 270 is to the right of 266, and 280 is to the right of 270. So to find the proportion of pregnancies that last between 270 and 280 days, then we look for the area under this model between 270 and 280. So let's first standardize our data so we find the z-scores for each of these number of days. So recall that the z-score is y minus mu divided by sigma. So the z-score for 270 is 270 minus 266 all over 16. And this will be 0.25. And the z-score for 280 is 280 minus 266 all over 16. And this will be 0.88, rounding to 2 decimals. And so now let's work with the standard normal curve, which has a mean of 0 and a standard deviation of 1. So we found that the z-scores were 0.25 and 0.88. And so the percentage of pregnancies that last between 270 and 280 days is the same as the area between our z-scores of 0.25 and 0.88. And so to find this area, we look up the z-score for 0.88 and subtract the area for a z-score of 0.25. So the area to the left of 0.88 minus the area to the left of 0.25. So looking up 0.88 and 0.25 in our z table, we find that the area for 0.88 is 0.8106, and the area to the left of 0.25 is 0.5987. And if we subtract these two areas, we get 0.2119. And so the percentage of pregnancies that last between 270 and 280 days is 21.19%. So at least how many days should the longest 25 of all pregnancies last? So here we're given the area underneath the normal curve. So the longest 25% of all pregnancies corresponds to a right tail area of 0.25. And we're looking for the number of days that this area corresponds to. So the area to the right of this value of y is 0.25. So we can work with the standard normal curve and determine the corresponding z-score for this area. We'll call this z star. And the area to the right of z star is 0.25. Now because our z-table only gives us areas to the left of z-scores, we need to determine the area to the left of z star by using the complement rule. So if the area to the right of z star is 0.25, then the area to the left is 1 minus 0.25, which is 0.75. So what we want to do is look up the two closest values to 0.75 inside of the z-table. So using the z-table, the two closest values are 0.7486 and 0.7517. So let's write down their corresponding z-scores. So we're given that the area to the left of 0.67 is equal to 0.7486, and the area to the left of 0.68 is 0.7517. So notice that 0.75 is almost in between these values, and so we will take the average of their z-scores to find z star. So z star is 0.67 plus 0.68 all over 2, and this will be 0.675. And now we can use our z-score to find the value of y. So our z-score was 0.675. We are looking for y. The mean is 266, and the standard deviation is 15. So rearranging and solving for y, we get 0.675 times 15 is equal to y minus 266. And so y is 0.675 times 15 plus 266. And this is 276.8. And so the longest 25% of all pregnancies last at least 276.8 days. Suppose a certain obstetrician is currently providing prenatal care to 60 pregnant women. Let y bar represent the mean length of their pregnancies. According to the central limit theorem, what is the distribution of this sample mean? Well, we're given that the duration of human pregnancies is described by a normal model. So the population distribution is normal. And the central limit theorem says that the sampling distribution will also be normal regardless of the sample size. So since the population distribution is normal, the sampling distribution will also be normal. Now the mean of the sampling distribution, which we denote by mu sub y bar, is the same as the population mean. Okay, so the mean of the sampling distribution will also be at 266 days. Now the standard deviation for the sampling distribution is given by sigma over the square root of n. So the standard deviation for the population was 16 days. And the sample size was 60. And so the standard deviation will be approximately 2.065, 59111, and so on. So what is the probability that the mean duration of these patients' pregnancies will be less than 260 days? Since we're looking for the probability of the mean duration of 60 patients, then we want to use the sampling distribution for the mean. So from part C, we're given that the sampling distribution is normal. The mean is the same as the population mean, which is 266. And the standard deviation for the sampling distribution was 2.0655. So we're looking for the probability that the mean duration is less than 260 days. So to find this probability, we want to find the area to the left of 260. So rather than working with this normal model, let's standardize by using our z-score formula and work with the standard normal curve. So the z-score for the sample mean is given by y bar minus mu divided by the standard deviation for the sample distribution, or sampling distribution. So the mean duration is 260, the mean is 266, and the standard deviation from part C was 2.06, 559111, and this will be approximately negative 2.90, rounding to 2 decimals. And so under the standard normal curve, which has a mean of 0, we calculated the z-score to be negative 2.90. And so the probability that the mean duration is less than 260 days is the same as the area to the left of a z-score of negative 2.90. So looking up negative 2.90 in our z-table gives us a left area of 0.0019. And so the probability that the mean duration of human pregnancies, or I guess these patients' pregnancies, is less than 260 days is 0.19%. In the next exercise, suppose that we play a game where we roll a die and we win nothing if the result is odd. We win $1 if we roll a 2 or a 4, and we win $10 if we roll a 6. So let's find the expected value and the standard deviation of our prospective winnings. So here our random variable x is going to be our winnings. And let's find the probability distribution. So we can win nothing if the outcome is an odd number, so either a 1, 3, or a 5. We can win $1 if the result is a 2 or a 4, and we win $10 if we roll a 6. So now let's find the probabilities for each of our values of our random variable. So for $0, we have a 3 out of 6 probability, which can be simplified to 1/2. For $1, we have a 2 out of 6 probability, which can be simplified to 1/3. And for $10, we have a 1 out of 6 chance. So now to find the expected value, or the mean, of our random variable, we take the sum of x times p of x. So we can win $0 with a probability of 1/2 plus $1 times a probability of 1/3 plus $10 times a probability of 1/6. And if you perform this calculation, we end up with $2. So we can expect to win on average $2 per game. Now to find the standard deviation, we first calculate the variance, which is the sum of x minus mu squared times p of x. So we have 0 minus 2 squared times its corresponding probability of 1/2 plus 1 minus 2 squared times a probability of 1/3 plus 10 minus 2 squared times a probability of 1/6. And this gives us a variance of 13. And now we can find the standard deviation by taking the square root of the variance. And the square root of 13, rounding to 2 decimals, is $3.61. Now let's suppose that we play twice, what is the mean and standard deviation of our total winnings? So here we're going to let x1 and x2 be the winnings for each game. And so our total winnings, we'll let that be capital T, is the sum of x1 and x2. So we want to find the expected value, or the mean, of our total winnings, as well as the standard deviation. So the mean of our total winnings is the mean of x1 plus x2, and using properties of the expected value, this is equal to the mean of x1 plus the mean of x2. And from part A, we calculated the expected value to be equal to $2. So we should expect $2 for the first game and $2 for the second game. And this will give us a total of $4. Now to find the standard deviation of our total winnings, we want to find the variance of the total, which is the variance of x1 plus x2. And using properties of the variance, this is equal to the variance of x1 plus the variance of x2. And from part A, we found that the variance was equal to 13. So this becomes 13 plus 13, which gives us 26 as our total variance. So now we can calculate the standard deviation of the total winnings, which is the square root of the variance of our total. So the square root of 26 is approximately $5.10. Now let's suppose that we play 40 times. What is the probability that we win at least $100? So here, let's let x bar be our average winnings. And if we want to find the probability that we win at least $100 over 40 games, then how much on average do we need to win per game so that we get at least $100 in total? Well, to find the average over 40 games that we want to win, we're going to take $100 and divide it by 40. And this will give us $2.50. So if we win at least $2.50 per game, then our total winnings will be at least $100. Since we want to find the probability of our average winnings, then we want to use the sampling distribution model. And here our sample size is the number of games that we play, which is equal to 40. So the sampling distribution model will have a mean which is equal to the population mean. And from part A, we calculated the mean to be $2. The standard deviation of the sampling distribution is the population standard deviation over the square root of the sample size. And from part A, we calculated the standard deviation to be $3.61, and we divide this over the square root of 40. And this will give us approximately 0.57, and so on. So now let's use our model to determine the probability. So the mean of the sampling distribution is at $2, and we want to find the probability that we win at least $2.50 per game. So this corresponds to the area to the right of 2.5. So now let's standardize into z-scores. So we take x bar, we subtract the mean, and we divide by the standard deviation of the sampling distribution. So here we have 2.5 minus 2 all over 0.57, and rounding to 2 decimals, this will be approximately 0.88. So under the standard normal distribution, which has a mean of 0, we calculated our z-score to be 0.88. And so the probability that our average winnings is at least $2.50 is the same as the area to the right of a z-score of 0.88. Since we want the area to the right, we need to use the complement rule and take 1 minus the area to the left of 0.88. So looking up 0.88 in our z-table, we get 0.8106, and if we subtract it from 1, we get 0.1894. And so the probability that we win at least $100 is 18.94%. In the next example, suppose that the distribution of the exam scores is normal with a mean of 18.6 and a standard deviation of 5.9. So what is the probability that a randomly selected student has a score of 21 or higher? So let's first draw our model. So the mean of our distribution is at 18.6, and the standard deviation is 5.9. And we want the probability that a randomly selected student scores 21 or higher. So to find the probability, we want to look for the area under the normal distribution to the right of 21. So let's first standardize into z-scores. So we subtract the mean and divide by the standard deviation. So the z-score for 21 is 21 minus 18.6 all over 5.9, and this will be approximately 0.41, rounding to 2 decimals. And so now let's work with the standard normal distribution that has a mean of 0. So we calculated our z-score to be 0.41. So we want to find the area to the right of this z-score. So the probability that a selected student scores 21 or higher is the same as the area under the standard normal distribution to the right of 0.41. So now let's use the complement rule to determine this area. So this is equal to 1 minus the area to the left of 0.41. So looking up 0.41 in our z table gives us 0.6591, and if we subtract it from 1 we get 0.3409. So the probability that a randomly selected student scored 21 or higher is 34.09%. Now let's consider taking a simple random sample of 50 students. What is the mean and standard deviation of the sampling distribution, and describe the shape? Well, we're given that the distribution of exam scores is normal, so the population distribution is normal. And by the central limit theorem, we know that the sampling distribution will also be normal. The mean of the sampling distribution is equal to the population mean, which was 18.6, and the standard deviation of the sampling distribution is the population standard deviation over the square root of the sample size. So the population standard deviation was 5.9, and our sample is 50 students. So 5.9 over the root of 50 will be approximately 0.8344, and so on. Now, what is the probability that the mean score is 21 or higher? Since we want to find the probability of the mean score, we want to use the sampling distribution model. So the model will be normal. The mean is the same as the population mean, which is 18.6, but the standard deviation is 0.8344. So we want to find the probability that the mean score is 21 or higher, which is the area to the right of 21 under the sampling distribution. So let's standardize using our z-score formula. We take the average minus the mean over the standard deviation of the sampling distribution. So we want the mean score to be 21. We subtract the mean of 18.6, and we divide by the standard deviation of 0.8344. And rounding to 2 decimals, this will be approximately 2.88. And so under the standard normal curve, we want to look for the area to the right of our z-score of 2.88. And so the probability that the mean score is 21 or higher is the same as the area to the right of a z-score of 2.88. And using the complement rule, this is 1 minus the area to the left of 2.88. And looking up 2.88 in our z-table gives us 0.9980. And we subtract this from 1, which gives us 0.0020. And so the probability that the mean score is 21 or higher is 0.2%. So now let's summarize what we've learned about the sampling distributions. When we have categorical data, we can calculate a sample proportion p hat, and the sampling distribution of this random variable will be approximately normal. It will have a mean, which is equal to the population proportion p, and its standard deviation will be given by this square root formula. And this will be true as long as we have a large enough sample, so it satisfies the success and failure condition. And so the sample proportion will be approximately normal. The mean is at p, and the standard deviation given by the square root formula. Now when we have numerical data, then we can calculate a sample mean y bar, and its sampling distribution of this random variable will be approximately normal and will have the mean that is the same as the population mean mu, and its standard deviation given by sigma over the root of n. And we had two cases to consider depending on the original population. If the original population is normal, then its sampling distribution will also be normal. However, if the population distribution is not normal, then as long as the sample size is at least 30, then the sampling distribution will be approximately normal. And this will conclude our lesson for this video. In the next video, we will begin to cover inferential statistics by talking about confidence intervals for a proportion. And I'll see you then.